Hello, good morning, good afternoon to everyone. Thanks for joining to my talk. Thanks for the introduction. Maybe I can just hold it with my hand. Yes, perfect, even better. Thanks to the organizers for inviting me. It's a big pleasure. So the title of my presentation, as you can see, is the Anticipatory Control of Human-Robot Interaction. But what I will be talking about is like how we are building with my guys in the lab, the elements that push us and motivate us toward building interaction autonomy for robots that are supposed to interact with the environment and the humans. So this is an image we've created over the past years before we arrive to full autonomy for our robotic and automation systems, that most of these human-robot interactions can also be automated. I think for the next tens of years, we will have this scenario, and we are pushing towards creating hybrid systems. Robotic systems, flexible robotic systems, and traditional automation come in contact with humans and robots, and the environment are actually in a close physical and social interaction. So what's really important, and one of the most key features that you can see, is of course, the interaction which is happening between robots, as I was mentioning, the traditional automation and robots. So the talk here is focusing on how we can actually boost this interaction autonomy on our robots. So if you think about, we look at this problem from a macro perspective, it's a naive presentation, of course. We have the corpus, which is the robot, interfaces, learning, control, everything that collects the way that corpus interacts with the environment and the human factors. So starting from the first, let's say, closing the loop, the easiest way to perform, create an interaction autonomy towards the environment is to close the loop through visual perception, right? So what do we do usually? We have really nice, reliable, nice perception systems that we are also developing in the lab that to the environmental variations, we detect the variations and we plan accordingly for grasping randomly thrown objects or objects that are put one on top of each other, right? So this has been really nice, and most of the approaches are like this: one-shot perception, planning, and manipulation. Perception is one way, visual perception, but of course it's not enough. Most of the cases we are also interacting through touch. For instance, for a blindfolded robot, we want to increase its interaction autonomy only through touch. Believe it or not, planning impedance and planning interaction is really, really important to make your robot plan autonomously. Let me give you an example. So if someone wants to pass a wire from a hole there to a hole coming up from there, you don't really know what's the path, and you don't have to plan for the trajectory. You just pushes the fishing wire with the wire attached to it, and it finds its way out. And how it works, it's actually some sort of impedance planning embedded to it. The ones that are familiar with the concept of impedance control, and especially when we represent the impedance stiffness and damping at the Cartesian, both for translational and rotational with the stiffness ellipsoid. So what you can do through singular value decomposition, you can know in which direction, what type of stiffness and damping you're applying. And you can actually plan for this in advance and have some principles that can help you towards a better interaction autonomy. So it's really nice that we only need 2 points while the robot is moving around the environment to be able to replan. So the main, let's say, rule is to be stiff in the direction of the movement, stiff enough, and compliant in the rest of the directions, so the constraints coming from the environment can help you navigate without seeing the environment. So if you have the first contact, since you're stiff here, the rest of the compliance will let you comply with the environment and move along. You will arrive here. Through these 2 points, you can actually update your stiffness ellipsoid and damping ellipsoid if you want to do also inertia shaping, the whole impedance parameters, and you can move and finalize the path. We need to actually plan for some sort of unexpected, really rigid constraints, and we have implemented some bouncing strategies to perform this task. So you can see this is one example that we did with Yasu and Toshi and my guys in the lab. So what happens here that you can see, only through interaction, the robot finds its own way, here. On these 2 columns, we have the same planner, but with low and high constant impedance values. Even though it tries to find its way out, but impedance planning seems to be really important. You can see the ellipsoid is changing according to the contact forces that which is perceiving and going through the path. Also, when it comes to the external disturbances, it seems to be very effective. So someone might tell, oh, okay, also in terms of interaction with people, robots this is really a good communication channel to boost robot autonomy. So today's robots are torque controlled. Even if you have velocity controlled robots, you can put skins that we developed around our Mocha robot. And you can see the people, Juanma and Mattia here, are touching the robot from any point, and the robot is complying with that. Since as I was mentioning, since touch is the lowest important, let's say, layer for interaction and ensuring safety, we have also embedded this in our planners. So if something goes wrong, the robot can replan through touch. Someone might say, okay, now we have perception through vision and touch. Why don't we just combine them together? It turns out, of course, it's a great idea. We have been working on this. Everybody have been working on this for a long time. For instance, through vision, you can detect a box. You can grasp it from its geometric center. But what happens when the center of mass of the box is changing? So you can actually measure this through your torque sensor, replan, and improve the reliability of your interaction planner and your interaction with the external environment. So the robot has no idea what's happening. It grasps, detects the changes of the, let's say, center of mass of the box on the fly, and grasps it from where the center of mass of the object is, not the geometrical. So it actually improves the robustness of your interaction autonomy. But quite frankly speaking, it's way beyond just combining visual perception and just touch. So actually it's not a plus, it's more of a regulator, and it depends on how much confidence you have on the sources of information that you get from vision or force torque sensor or haptic data. There's a lot of sources of uncertainty that tells you which source to which one of them are more reliable. You can have uncertainty, visual perception, calibration, modeling error, latency, control errors, and disturbances. Just to give you one quick example. Imagine you have a robot, you do a single shot planning based on visual perception, and the robot goes and picks an object with algorithm 1, and it goes towards the second object, and it ends up in algorithm 2. And you might say, which algorithm performs better? Everybody will say algorithm 1. Most probably yes, but probably also not, because maybe all the uncertainties of the system are in favor of algorithm 1, which is working worse than algorithm 2. So maybe algorithm 2 is more globally valid than algorithm 1, and you were just lucky that uncertainties of the system, just simply uncalibrated robot, is helping you to arrive to point 1. So we get into this more in detail. For instance, in a really complicated box item sorting, which you can see, it's one of the use cases in the Sophia project that I'm coordinating. This is really complicated because there's a lot of uncertainty, the placement of the box, the way the objects are placed there. But what is really nice that we did some experiments when people don't have so much confidence on their visual perception or their attention is deviated. So we usually exploit the impedance planning that I was mentioning in the beginning, and we exploit environmental constraints. And where we start, so we place the object, you slide it towards the final goal, and where you start and how much the length of that will be, it depends on how much confidence you have on your visual perception. If your visual perception is super strong, you can actually do pick and place the way actually currently industrial robots are doing. So bringing into robotic application, as you can see here, the robot is actually intentionally added some noise to our visual perception. You can see the robot is actually taking this through the occupancy grid map. It plans where it should start, slide through impedance planning that I was mentioning to you, exploit the environmental constraints to perform this planning and perform this complex, interactive, contact-rich tasks without really a super fancy position planning or trajectory planning involved. So this robot is not, this algorithm is not designed to be collaborative, but at the core of it, since you're complying and you're responding to the external disturbances coming from the environment, you saw Pietro change the position of the box, visual perception captured it, but maybe there's some level of uncertainty to it. And then you can also capture if the objects are being added or not. So the robot is actually adding and responding to that on the fly. So there's no need to basically reprogram everything, because you can just, tune your confidence towards different perception sources that you have. Even if you have different objects inside the box and you're asking to resort it, you can see really nicely through visual perception plus planning through touch. You can simply replan them, even if you can create collaborative systems without even knowing that you're creating collaborative systems. Pietro feels like contributing, and he puts some more objects, and the robot replans and makes actually the thing faster. So just to give you an example, if you don't do impedance tuning with everything else included, so in a certain phase that you're actually you're sliding towards putting this object here, when the contact will be here, you have a rigid constraint. And if you're rigid in all directions, you will have high interaction forces, which happens in without self-tuning, and the robot triggers the fault. You might even damage the environment. But at the other hand, on the other hand, if you're compliant, and as I was mentioning, you can perform it and respond to the uncertainties that come from the planning task or the environment. The balancing visual feedback and visual information and touch is also really important to go beyond what I was mentioning. For instance, in collaborative, let's say co-carrying, what we usually do, we build our admittance causality based on what the human is applying. Do and I is applying some forces here. Robot responds through whole body admittance controller, plans torques and virtual torques for the environment. But what happens if you have a rope? It's flexible, right? So you cannot really get information in these directions. And the information that you get, the force information you get in some directions are imperfect. In a sense, you will see here, you need to push so that you can feel some forces that you can move it along. You might say, okay, let's just do some sort of teleoperation locally. You just watch the person to move. It works, of course, for the robot, but it's not going to work for this because you have to create some movement before you are able to go. And especially when you have partially deformable objects and you don't want to model them because it's useless, you can actually respond to that. So we kind of started to look into this. It's more elaborate than that. Please do have a look at the papers, and we have one presentation in this direction as well. What we do, we are actually on the fly, in real time, you're looking at how much information we are getting from the vision and force, and adaptively we configure our controller based on that. So one of the PhD students passed away. No, I'm kidding, of course. So this is just a mannequin, and as you can see, Doanai is moving the robot. It's a very flexible, let's say, material. And you can see through the intention, through posture, you can do not only translation, but also rotation. It's quite nice. The controller has no clue what you're carrying. It can be a rigid, flexible, semi-rigid, semi-flexible, also directionally different, and you can actually perform these tasks. So we also, as I mentioned, did some testing on semi-flexible objects, and it turns out that you're actually applying less force even on rigid, in semi-rigid cases, and it's easier and it's more effort in terms of effort is more reliable to carry objects from a point to another point. So we didn't stop there. There's this probably you know that to carry non-graspable, really bulky and rigid, heavy objects, you can actually use these straps. So the same technique works actually for multi-robot control, and through this, Idil here is actually co-carrying this large box, and the robot is only reflecting all the twist and wrench that is basically at its end effector, and according to our planner is moving and helping Idil to go up and down, left and right, rotate and all that. Robot has no clue about what you're carrying, just like before, and has no clue about what the other robot is doing except just avoiding the collision. So this is a little bit of course, we are working more on that, but just to tell you a little bit of some stories about how we can make sure the interaction between robots and the environment is also effective. So just to tell, we've been doing some research over 5-6 years on this, but I'm going to walk you through a little bit of what we have been doing in physical and cognitive modeling of human intention. And our approach is look at the posture. Posture data is way beyond just movements of the people, and I will tell you how we are looking into this. So from the physical perspective, our approach of modeling humans is a humanoids based. So we started from whole body, let's say, control point of view, saying that, okay, you're in equilibrium condition, center of pressure is here, ground reaction forces. When you have an external force applied, center of pressure displaces, ground reaction forces changes, set up your whole body controller. We have some tricks there, 5 papers, please have a look at them, 4 actually. And then you will find out that what is the external what's the effect of external force on your joints? It's called overloading joint torque. And obviously, we wanted to calibrate and personalize this model through online models. This black shadow shows the minimum required information for you to build this model, whatever you need, once in a lifetime, unless you eat a lot and your center of mass varies. And you can see that after identification, which is a couple of maybe a minute or so. Then the model is built. So in real time, the person goes, you can see actually we set some risk levels. I hope you can see at the back as well. When Luca is going to pick this object, the overloading joint torques are shown. In real time, we can track them, but just to tell you, you can see the shoulder becomes red and stuff like that. So it tells you how much loading you're applying to the person. We had an assumption that the person is interacting with the hands. It's a valid assumption, but it's not always the case. Sometimes you're interacting with the external world through the elbow. So these are also really nice tools in robotics and humanoids theory that you can actually, through torque equilibrium, you can understand where the point of interaction is by setting up your equilibrium condition, torque equilibrium condition at the joints. But what's the bad thing about that is it gives you a line and it might collide with several joints. But since you're moving, you can build a probabilistic approach telling you that what's the likelihood of that particular link undergoing an interaction. And we built that using some techniques. And you can see here, Marta is actually doing just one video to show you. It's interacting with the elbow. You can see this is the famous line, sometimes colliding and stuff. But then you're building your probabilistic approach, and it understands, okay, the point of interaction should be at the forearm, and it builds up your overloading model and it updates that. So since now we can understand the contact, we added some more indexes. For instance, compressive forces. In robotics, we call them internal forces, especially people working on the grasping. Sometimes in some postures, these forces, you can see, have way more effects than the torques, obviously. The last thing so far we have done was, so our approach is to start from rigid body dynamics, reduce complexity, so we can use robotics technologies to model human physical behavior. But it's a little bit of oversimplification for the back, right? But what do we do now? We go start modeling OpenSim again. So we said, okay, let's just model the back, the spinal cord like a flexible beam. We know we have some knowledge from robotics. We built this model, we calibrated it, and actually you can see just a flexible beam gives you a very good, let's say, indication of how much compressive forces and torques is going across the back. Some indication was given on the physical factors. On the cognitive factors, we have a very similar approach. We're just watching people. No EEGs, no other sensors, no invasive sensors. So the whole point is, your body talks so loud that sometimes when you're saying stuff, it's against it. So this is Marta, and she's working on actually looking at how we can, first of all, understand the attention of the person by setting some frames on the face and the environment. You understand where the person is looking, and you can actually build your confidence level on the vision. If you're lacking attention, then your controller and planner should rely mostly on the haptic data, right? Going back to the first, you can actually see if the person is sleepy or a bit, some abnormal behaviors that you're not expecting to have that. To measure cognitive load, you're also looking at hyperactivities, such as self-touching, face touching here, or some hyperactivities that you know that somebody's moving the legs so fast, you know that somebody's, that person is kind of loaded cognitively. So putting everything together, these are just some examples that I was giving you. In addition to some other examples, you can actually build your model, and to give you, this model can give you in real time some indication of mental effort and stress levels, right? So obviously, as a ground truth, we compared this to galvanic skin response, heart rate variability, and some measures to make sure that this is actually what we are looking for. So now let's see how we can put everything together, including the controllers, and how we can actually anticipate the interaction that happens between humans, robots, and the environment. So for us roboticians, I think anticipation is nothing more than just setting up an optimization, a reinforcement learning, anything that you want based on the type of information that you have. Imagine that you just use your overloading joint torques that you have as a closed loop. You have an offline identification model, you're interacting with the environment, and then you can say, okay, I want to minimize these torques. I put it in a QP optimization, and I put it, let's say, some sort of weighting here. Whenever some joint torque increases, I will just automatically increase that torque. So I want to minimize that torque well. And this is subject to several constraints. Let's say your support polygon constraints, interaction constraints, external constraints, or whatever. And it anticipates and tells you what you're doing, probably you should be doing in this, let's say, configuration, which is the configuration that minimizes the effect of this load on the joints, and it actually doesn't let one single joint to be overloaded. Just to give you an example, this is our early version of Mocha robot. It goes towards Marta. Here it recognizes just an object. So it's going to be just a handover. And the only objective we are setting there, except all the joint limits, stability and stuff, is just overloading joint torque. So it's basically what we anticipate to arrive, what the robot anticipates to arrive as the most ergonomic, let's say, posture. But then Mansu comes in with a drill, and the robot sees that you have a tool that you want to interact with the robot, and it adds to the constraints that you have. For instance, if you have a power tool, you want to apply forces, you can actually increase the force manipulability, which means that in this posture, you need minimum torques at the joint to apply forces. You can actually elongate your ellipsoid in this direction or make it even isotropic, so you're more ready to respond to different, let's say, sorts of forces. So you can even bring the anticipation to a context level. So if, for instance, here Francesco is doing some ergonomic human-robot interaction, and then the robot knows that your next plan will be to go to point A, and uses its 2 degrees of redundancy to facilitate this for you. So you can go from point A to B without being have to go around the robot. So if you're interested, please look at those papers. When it's coming to ergonomic, let's say, human-robot interaction in terms of cognitive factors. So just to give you an idea, what we're doing, so imagine you're working with a robot in a box filling task. Your boss wants to do it as fast as possible, and it tells you, these are my performance indicators, these are my cost functions, and you have to go towards one. But your psychiatrist says, no, it's not true. You should work as slow as possible because I want you to be very smooth and calm. And then you're setting up this Pareto optimal front, let's say, optimization problem, and which point is supposed to be correct is depending on the state of that day, and also on a personalization aspect that we're looking at. So this is how you're moving across these points comes from the level of cognitive load, and the rest of it is basically some sort of planning that you will see in this video. So the robot initially captures some sort of rest state, and then so sees that the productivity is very low and starts pushing on the speed. When it's pushing on the speed, intentionally, we actually exaggerate it, and it's pushing so much, anticipates that it wants to arrive here, and eventually even harder, and arrives so fast that through some measures, we capture some higher cognitive load, and the robot sees that, oh, there's probably too much, I pushed too much, and goes back to a level of speed and a smoothness of the robot trajectories that basically it balances between the productivity, speed of production, and also cognitive levels. So to conclude, I would like to give you some key messages from this presentation. The first most important message is, this is very particular because we are in the era of machine learning, also in our lab we are doing, but we are sometimes neglecting the importance of impedance regulation in planning. Impedance regulation is not only for contact. Of course it is main let's say perspective of doing impedance regulation is to have a reliable contact, but you can use impedance regulation as part of your planning. So it can reduce basically your load on precise planning, and it can be used really to have reliable interaction with the human and the robot. That is why, and the example I was mentioning to you, we should not really trust either one of these sources, especially, for instance, most of the time we do single shot perception and then manipulation. We definitely need to do either continuous way of perceiving the scene to make sure that the uncertainties coming from the robot, the environment, contribute to high performances, or we can actually balance physiohaptic information depending on the level of confidence that we have for at the level of interaction. Physical human factors go beyond movements of the person. So you just move the body and you detect the posture. So you can actually get way more in depth in these factors, and you can actually get more, not only human physical factors, but also let's say cognitive factors. The last and very important thing, I was at ISRR giving a talk, and Osama Khatib said something that I've always been thinking about it, and now I feel more confident to say that. I think every robotic, let's say, algorithm we are developing, which is on a physical system, should be, even if it's not meant for touch, it should be evaluated in contact. Planning algorithms, anything that might even not eventually come to a contact, it should be evaluated in contact. It's important to understand what is the system's behavior across in response to the contact. That's it, and I am really honored to thank you very much, first of all. Well, these are the people I have the pleasure of working with. My main lab is at HRI2, at IIT, called HRI2. We are about 30 people. The second lab I am coordinating is Leonardo, which is called Robotics for Manufacturing. We are about 5-6 people there. I'm also PI of another joint lab, which is really close to industrial applications. And of course, I would like to acknowledge the funding of my research, some projects I'm coordinating, European and national projects. And thank you very much for your attention and coming to my talk.
Thank you very much. So is there any question, comment? Please raise your hand. And okay, so.
Hey, hi, Arash. Thanks a lot for this very nice talk. I have a question. You use mostly exocentric vision, so with camera that looks in the workspace. Do you think that a combination or using egocentric vision from the manipulator and the person it's himself or herself might change and add something to the algorithm and the safety overall?
Egocentric, you mean, for instance, the fisheye camera that is on the robot, like on the robot itself? Yes.
On the robot, you have a camera, but
yes.
You are mostly using camera also exocentrically.
Of course, of course. The whole point is, no matter where you put the camera, maybe it's connected to some level of uncertainty. So if you continuously watch where you're going, I think it's the solution. Maybe you can decrease the level of error that you have in the perception. For instance, what we are doing now, we are putting multi-cameras for human tracking, and we are modeling the uncertainty using Gaussian process for each camera. But still, you have some level of error with respect to really precise OptiTrack systems. So it's you either learn while you're moving, learn where the source of uncertainty is, and update your models, or use some other sources of information like touch. Probably could be an answer to that.
Okay.
Thank you, Lorenzo.
Thanks a lot.
Thanks
a lot.
Yeah, so any other question, comment?
There's you.
Yes, please.
Hi, thanks for the presentation. So I wanted to ask, in the collaborative load carrying task, using haptics, how can you manage the up and down motion? Because you mentioned that.
Very nice question. So quasi-statically, of course, if the movement is quasi-static, you can understand, model the gravitational forces by looking at how much force is applied in the direction, and you can actually feed forward that. But since this is some sort of admittance controller, you don't respond to those forces, and the forces that come from the human, in addition to that, you will respond to this. Yes, I hope I answered your question.
Actually, I'm talking about the case where you are holding the rope, and like the gravitational effect doesn't change if you go up, if the human goes up and down.
We are not using gravitational effect there. So the controller is balancing there more towards the vision, so it becomes a local teleoperation. Since there you're not reflecting any forces. So you can imagine the controller is like on the far right side, it's a teleoperation. Locally, you move, the robot moves. On the most left side, it's just admittance-based co-carrying. You apply forces, the robot responds to you. But there's a whole spectrum of how we can combine the drift and wrench. And that is the adaptive part of putting things together without even knowing what the knowledge is.
Okay, so yes, go.
Thank you for the great talk. So I have a question. So you had mentioned that one way of inferring human intent is like during the collaboration task is like based upon the forces and the torque that the end effector is receiving. Could you expand upon like maybe how robust that is, and like have you ever like looked at like other modes of like inferring human intent like gaze and etc. And one more is how generalizable are these models that you're portraying? Is it like specific to each person and requires like a calibration process or something like that?
Thanks. Very nice questions. The first one, I think, it depends on the complexity. I'm not sure how can I answer that question, but I think the most reliable, the more modalities you add in terms of interaction to capture intent, the more robust your let's say planning and your basically reactive algorithm becomes. Visual perception and touch is one of them. Obviously, if you can build ways that you can do eye tracking and even temperature sensing and stuff, but the more you add features, it means it requires some sensory systems to be added, regardless of cost, but many of them come with variability, and variability is something, especially in industrial environments, are not really welcome. So if you put the eye tracking camera, people will start complaining. If you put the EEG, they start complaining. Even a watch might be something that they don't want to wear, you know. So it's a balance between how far you want to go and how much information you can get with really cheap and accessible information. The second question was extendability. We don't have an answer to this, but we are taking this to in our, let's say, use cases in European projects, in new things that we think that they are working. And most of the algorithms with a little bit of not tuning, but a little bit of rethinking work, the impedance planning, the tuning of the uncertainties based on the vision. Most of them work, but I can't tell you really this is the answer, or basically, obviously, this should be tested in several contexts. I didn't have time to talk about it, but we're bringing this in healthcare. So robots are assisting people that assist humans. I think this is a good step before we really start assisting humans. Assisting them turns out to be, these methods are also working in that direction.
Yes.
So you also mentioned healthcare. So I have like one more question, like, and it's probably a little more general. Like, a lot of it is you're talking a lot about autonomy. So I was wondering, like, how much would you look into like how explainable the autonomy is? Like, is it like how accepting or not accepting are people if the behavior of the robot cannot be easily predicted?
So the good news is the principles behind all these type of interaction autonomies are known, and we know we can expect what's going to happen because, or based on, I don't want to say control, but based on some principles that you can expect. So it's not data driven. And when we use data driven approaches, we are just tuning the parameters of the controllers that we know how to. So we use data driven approaches to know how to change the impedance behavior of the robot, but the impedance control is done through passive and through energy aware systems, that you make sure that the system is passive, it's stable, and the interaction is reliable. Maybe it's not optimum, but it's still reliable. So I think it's explainable, but to be honest, we haven't made this, let's say, put this in a really formal shape, how much we can explain the behavior of the system.
Thank you.
We can accept one more question.
It's over there, I think.
Yes, so please remove the cable
Hello.
to prepare for that.
Thank you for the inspiring talk. So just one question I had, when you're talking about combining visual information with haptics, do the rate of the sensors matter? Because you're getting visual sensing at a different rate than your touch sensing, right? So how do you kind of handle that problem?
Of course. So it's a very nice question. Thank you. It also depends on the level of interaction that you have. For instance, when you're interacting with humans, the maximum frequency you're expecting is about 10 hertz for detecting human body movements. But when you want to detect texture through touch, you want to go beyond kilohertz, because the high frequency information that you get, and you want to, for instance, also identify the friction, it changes. So the faster you go, the better, but it comes with some computational cost. But this is more of I think, an engineering issue. I don't know. I would tell you, go as fast as you can, but you would say my ROS is running on 100 hertz, and I want to detect a flying object. So there's some I think some approaches, estimation algorithms that you can tell a little bit what's happening in the future horizon can help. I'm not sure, to be honest, but of course, just to tell you, the different sources of information come with different frequencies, but you can actually eventually, based on how you're processing them, but the final controller will run in the frequency that your information is being updated. So it's synchronization is not a big issue there.
Okay, so it's time. So thank you very much.